Hi, what if I told you there exists a length so small, so fundamental, that it could redefine how we perceive the very fabric of the universe? I'm talking about the Planck length, the scale beneath which our known physics starts unraveling. The mysterious Planck length is considered one of the universe's most fundamental constants. But there's so much more to it than meets the eye. Today, we will journey into the uncharted territory of this incredibly minuscule realm and explore its deep implications for quantum physics, relativity, and the quest for a grand unified theory of everything. Let's dive in. To fully appreciate what the Planck length represents, we need to scale down our imagination. Imagine dividing a meter into 1,000 millimeters. Then, each millimeter into 1,000 micrometers, and each micrometer into 1,000 nanometers. Keep going. From nanometers to picometers, to femtometers, and further into scales that seem utterly incomprehensible. When we reach the Planck length, which is roughly 1.6 times 10 to the power of negative 35 meters, we are at a dimension smaller than any physical object we can currently measure, even smaller than the elementary particles that make up everything in our universe. Some say this is the smallest meaningful unit of space itself, a domain so far outside ordinary experience it's practically abstract. Why this scale? Here's the thing. The Planck length isn't just some arbitrary measurement. It's derived by combining three fundamental physical constants: the speed of light, the universal gravitational constant, and Planck's constant. These constants form the building blocks of both quantum mechanics and general relativity. The result of this combination is a natural unit of length that genuinely operates as a limit, a kind of border wall between classical and quantum realms. In scientific terms, when distances get smaller than the Planck length, our equations for spacetime stop giving us realistic or even usable answers. Many physicists interpret this as the point where our concepts of distance and spacetime cease to make sense in the usual way. Now you may ask, does this mean there's nothing smaller than the Planck length? Maybe. But here's where things get even more interesting. If you shrink something smaller and smaller, down to a Planck length or beyond, quantum fluctuations start wreaking havoc. At the Planck scale, it's hypothesized that spacetime doesn't behave smoothly, like a continuous fabric, but instead resembles a chaotic, foamy structure made of unpredictable quantum jitter, a phenomenon often referred to as quantum spacetime foam. Essentially, this means that spacetime at the Planck scale may be far from flat, but bubbling and twisting with random fluctuations that blur the line between geometry and randomness. And this is precisely where the Planck length draws us to the deepest mysteries of contemporary physics. You see, one of the cornerstone challenges of modern science is unifying two titans, quantum mechanics and Einstein's general relativity. Remarkably, what might bring these two conflicting branches of physics together is the Planck length. General relativity describes the cosmos on grand cosmic scales, from galactic clusters to black holes. Meanwhile, quantum mechanics elucidates the physics of subatomic particles. But here's the kicker. The principles of relativity break down at the quantum scale, and vice versa. Right at the Planck length, both quantum effects and gravitational effects become equally dominant. This is the domain of quantum gravity. And yet, this mysterious length scale continues to elude direct study. Now, let's talk about theories. In string theory, a leading candidate to solve quantum gravity, the Planck length plays an especially foundational role. According to string theorists, what we perceive as particles are not actually tiny points, but rather one-dimensional vibrating strings. And these strings have a fundamental size on the order of the Planck length. This means the Planck scale might be the emergency exit to a much higher dimensional reality, where the laws of the universe operate in completely unanticipated ways. Similarly, loop quantum gravity suggests that spacetime itself might be composed of indivisible discrete units, like atoms of spacetime. And guess what? The volume of these units would be determined by the Planck scale. These ideas completely upend our understanding of spacetime as a smooth and continuous entity. They propose that at the smallest scales, space might be granular. And of course, I can't talk about the Planck length without delving into the topic of black holes. Enter the wondrous world of the Schwarzschild radius, the point where gravity becomes so intense it traps light. Now, imagine squeezing an object so densely that its Schwarzschild radius shrinks to the size of the Planck length. This is what physicists call a Planck scale black hole, and it represents the ultimate paradox, a domain simultaneously governed by extreme quantum mechanical rules and overwhelmingly powerful gravitational forces. It has been theorized that this extreme convergence might hint at the existence of holography, where information doesn't just exist in space, but is stored on the two-dimensional surface bounding the system. Holography might even reveal how space-time itself gets born out of quantum mechanics. Stepping back from the technical depths for a moment, I want us to think about the philosophical implications of the Planck length, because here lies one of my favorite aspects of physics. Isn't it beautiful, but also perplexing, that nature imposes limits like this? And what does it even mean for the universe to have an elemental fabric at all? If distances below the Planck length have no meaning, could this limit be saying that space has a kind of pixelated structure, a minimum resolution, if you will? Or perhaps, could it even suggest that space is merely an emergent property, a mirage born out of information or something else entirely? But the real beauty here is not just what we know, but what we don't. Why should the universe even have a fundamental length scale like the Planck length? Why do these constants converge in such a specific, almost elegant way? Without experimental tools to probe it directly, these remain profound speculative questions. However, this same unknowability holds promise. One day we might develop ingenious new methods of observation, powerful enough to peer into this abyss of reality. Perhaps these studies would show us what the universe is woven from, or confirm whether space-time is just a part of an even vaster, hidden structure. So here's my challenge for you. What do you think lies beyond the Planck scale? Could the Planck length become the bridge that unites quantum mechanics and gravity once and for all? Is space-time an illusion, or is it the universe's most intrinsic quality? Make sure to share your thoughts in the comment section below. I would also love to hear about your favorite theories or ideas involving the Planck scale. Trust me, your contributions might spark the next big conversation. Before we part, a quick summary. The Planck length isn't just a physics trivia point. It's likely the meeting ground of classical and quantum principles, the smallest viable building block of reality, and a clue to the mysteries that physicists are dying to unravel. If you leave this video with more questions and awe, that means we've done our job here at Hyperfocus, Advanced Physics Dialogues. Thank you for expanding the universe of your mind with us. Till next time, stay deeply curious.